I'm Mark Hopkins. I'm Senior Vice President of the National Space Society. And this press conference is being organized basically for two purposes. The first is to provide support for the Discovery Channel's TV program on space solar power. And this is going to be broadcast for the first time tonight at 10 p.m. local time. And so you can watch that. It's a very interesting program. And the second reason is because the National Space Society strongly endorses the basic concept of space solar power as something that we should look into because of its enormous potential for the United States and for the world as a whole. What we're talking about here, the core of this, of the Discovery Channel program tonight, and also this press conference, is a demonstration of space solar power technology, which has been kept under the wraps until now. I won't discuss this in any detail because we have the person who led this effort, John Menkins, here, and he will be discussing this a little bit later. What I'm going to do is give a brief description of space solar power, the overall architecture, and then I will discuss why space solar power, if it works out, is of such tremendous importance to this country and potentially the world. Space solar power, we have a little demo up here, which is on a loop. Basically, there's a lot of different possible architectures, a lot of different ideas about how to do space solar power, which is one of the strengths of the concept, because that means that if one of these approaches doesn't work out, we can try another one. Sort of base case situation is demonstrated by this video. You have solar cells in space. They collect energy from the sun, convert it into a very low intensity microwave beam, and then send it down to the Earth, where it's collected on a rectenna, and then this is fed into the power grid and gives us electricity. And I'll walk you through it on the next loop here. One of the things which, here we go. This is one concept of space solar power. And in this particular concept, we not only have solar cells, which are down here, we have mirrors in space, which concentrate the energy of the sun onto the solar cells. And the reason for that is the mirrors are relatively inexpensive, and the solar cells are relatively expensive. As a consequence, if you can concentrate some of the sun's energy on the solar cells, then that makes more economic sense. The power comes down, actually not in these loops. It hits the rectenna, which is that green thing, converted into electricity, and it goes over to the city to power it. Could you turn off?
Sure. We'll turn this on.
Yeah. I think we've seen that a number of times. One of the questions which frequently comes up is how to turn it off.
It's relentless.
There's the plug down there.
No, don't pull the plug. I need the plug.
Don't pull the plug. Sorry.
If you pull out the headset jack.
I didn't mind
How about
the
a
video.
skate?
Yeah, the picture's okay. Sound.
Or just mute it. The laptop.
You were right, but I tell you.
One of the questions which frequently comes up concerning space solar power is, well, look, it's clear that doing things in space are more expensive than doing things on the ground in general. So why does it make sense to put solar cells in space rather than on the ground? And there are basically two main reasons why this may well make sense. One is that the intensity of sunlight in space is a lot greater than it is on the ground, roughly a factor of 7. And the reason for that is first that when the sunlight goes through the atmosphere, you lose some of the energy. And secondly, there is, at any given point on Earth, from time to time, you have bad weather, and as a consequence, you get less solar energy. And the third reason is because you have the day-night cycle, and you obviously don't get solar energy during the night. In space, you have the sun shines on these space solar power satellites virtually 100% of the time, and you obviously don't have bad weather, so or an atmosphere to deal with. So these problems don't exist. The other big thing is that if you have a power grid on the Earth, and it's mainly based on solar power that's on the Earth, then that means you have to store a great deal of energy in order to take care of your energy needs at night and during periods that are hard to predict of poor weather. But if you have a space solar power satellite, since you're sending on the power all the time, and this beam is at a frequency which will go through bad weather without any significant problem, then you don't have this storage issue. Now, one of the main reasons that space solar power is of such interest is because its enormous potential size. The amount of power which can be produced by, say, solar power is potentially greater than that of all other energy options combined. And it's quite sufficient to take care of all of our current energy needs, or not only this country, but the human race as a whole. And to continue to do that, even if the demands for energy, as is likely the case, increase substantially over time. There's also the potentially the greenest of all the energy options, maybe even greener than space-based solar power, ground-based solar power. And on the long run, that is even more true than in the early situation. And for example, the case, it has very low carbon footprint, and as a consequence has no significant impact on global warming. Indeed, if we were consuming only space-based solar power today for energy throughout the world, it's highly likely that there would not be a climate issue. Now let's look at the larger picture and see how space solar power can really impact the future of the human race. The average per capita income in the world today is a factor of 7 below what it is in the United States. Sometimes we in this country don't quite realize how poor most people are. Now that's the average, factor of 7. That's like factor of 2 below the poverty line in the United States. Poor people, by human standards, are a lot worse off than that. In fact, the bottom 1/4 of the human race doesn't even have electricity. Think about that. Doesn't even have electricity. They're very poor. One of the things that we would like to do for the human race over the long run is to increase our standard of living, say, up to what it is in the United States today, at least. If we do that, what does that mean? Let's assume that we just look at an analysis where we assume that the human race doesn't increase in size beyond what it is currently, and further assume that the energy that the United States and other industrialized countries per capita does not increase. That means we have to increase the global human economy by a factor of 7. Now, if you take into consideration that the human race is obviously increasing in size, and that the per capita energy consumption of the United States and other industrialized countries is also increasing, then that number goes up again. So, where are we going to get that kind of energy, and get that kind of energy in a way which is environmentally benign? And we need a very large amount of energy, and space solar power has potential of providing that and far more. Indeed, the sun currently puts out between 1 and 10 trillion times the amount of energy that the human race currently consumes. That's a trillion with a T, not an M as in a million, or a B as in a billion, but a trillion as in a T. That number is so large that if every person alive today consumed an amount of energy which is equal to the entire amount that the human race currently consumes, we would still only be consuming a small fraction of what the sun puts out. That gives you an idea of the long-range potential of this concept. Why? Let's look at the situation with regards to other countries. The United States is by far the world's greatest space power. We spend more on space in this country than every other country in the world combined. And when it comes to thinking about any major space program, it makes far more sense for the United States as a rule of thumb to do it than other countries, simply because we're so far ahead of everybody else. And yet, we're not spending any money in this country on space solar power. Oh, there's some organizations that are spending some internal funds. But no, the government is currently not funding anything. This is not the case in, say, Japan, where they've had a government-funded program for like the last 10 or 15 years. It's not the case in Europe, where they also have a government-funded program. The situation is ridiculous. If space solar power makes sense, then the United States should be doing it because it makes more sense for us to do it than Japan or Europe. Hopefully, in the next Congress and the next administration, this situation, which is a major failure of our current energy program, current energy efforts in the United States, will be rectified. Another thing that we have to worry about, and there's increasing interest in the Defense Department concerning this issue, is the potential of energy wars in the future. If we continue to have dwindling supplies of energy, if the amount of energy, the price of energy continues to rise, if this energy is controlled by powers which are hostile to the United States, which seems to be increasingly the case, and hostile to our allies, potentiality for military conflict goes up substantially. If we have, alternatively, a major abundant source of electricity, so great that it can solve our energy problems, not only for the United States, but for the world as a whole, then this problem evaporates. We've heard a lot about, in the campaign, energy independence. And why is that? Because we're in this ridiculous situation where we're sending like $700 billion a year abroad to import energy. Much of this goes to powers which are hostile to the United States. And some of it is being used currently to fund terrorists who are fighting the United States. We need to eliminate this problem. And if you have the sort of energy we're talking about here with space-based solar power, then that is far more than enough energy to obtain energy independence in the United States. In fact, the situation is even better because we can not only obtain energy from the United States, we can become a major net exporter of energy, as was the case for the United States before 1950. But in a much bigger sense, we can become, in the future, a more dominant energy player than Saudi Arabia is today. Why is that? Look, what you're doing, what we can potentially do, is build space solar power satellites using American workers in the United States. Launch these into space using American workers that build the rockets to do this launching. And then these satellites, they can be powered anywhere in the world, not just the United States. So they could beam it to other countries and become a major export product. The potential of space solar power is so large that if it works out, then it would transform the American economy to a far greater extent than, say, the auto industry did in the early part of the 20th century. Space solar power is not only a method for making Americans far better off than they are today, but it's also something that America can do for the world as a whole. Because the energy crisis is not just an American problem, it is a world problem. And we can solve it with space solar power. And climate change is not just an American problem, it is a world problem. And if all of your energy is being produced by a method which does not cause climate problems, then this would be a major step in eliminating the problem of global warming. Now, I'm going to hold the questions until the end. The next thing we're going to do is we're going to play a piece, short piece, of the program that the Discovery Channel will present tonight at 10 o'clock p.m.
Scientist John Mankins believes the end of our dependence on fossil fuels could begin in space. 174 million gigawatts of solar radiation hits the Earth every second. That's more energy than our civilization's used since the dawn of the electrical age. Solar technologies are turning more of that energy into electricity than ever before, but their effectiveness is limited by two major factors. The first is our atmosphere. It either absorbs or scatters 50% of all solar energy before it hits the ground. The second is more obvious. Ground-based panels collect less energy when skies are overcast, and nothing at all when the sun goes down. But the sun never sets in space. 24/7, second by second, it beams energy towards Earth equal to the output of 1 billion large power plants.
And if we can somehow capture that enormous amount of energy which is flowing past the Earth constantly, then we can truly transform our energy situation here on Earth.
Mankins wants to launch an array of revolutionary solar cells into orbit 22,000 miles above the Earth. Spread over a mile grid, they'll harvest the maximum power of the sun. The solar energy would then be transmitted through harmless forms of focused microwaves down to giant receiving stations on the ground. These receivers, hundreds on every continent, would convert the microwave beam into electricity. The potential for harvesting energy with Mankin's system, if it works, is almost inconceivable.
It's perhaps 10,000 times more than all the energy needed to drive society.
To see if Mankin's space-based strategy is technically possible, a special team from the Discovery Channel will conduct a series of scaled-down experiments.
I'm really interested in light and the efficiency of the solar panels.
Quantum physicist Basil Singer will test the science.
Let's go! Is this a big enough idea to replace fossil fuel for making electricity?
Global business executive Kevin O'Leary will work out the logistics needed to make the experiments happen.
That is beautiful.
Well, you mentioned the beam. Do we know the beam works?
And eco-designer Jennifer Langwell will explore cutting-edge microwave technologies needed to test Mankin's plan.
We are still transmitting.
What we'd like to do is a long-range test, form the beam, show that we can point it, show we can transfer energy, and do it over a long enough distance that it's similar to the kind of distances that you'd have coming down from space.
Okay.
Woohoo! NASA scientist as hero.
It's odd to watch.
That's a transformation for you too.
Yeah.
I'd like to thank the Discovery Channel for providing us with a copy of the program we're going to show tonight. That's just the first few minutes of it. And now I have the honor, and really is a great honor, of introducing John Mankins. He is Chief Operating Officer of Managed Energy Technologies. He's President of the Space Power Association. He has a 25-year career at NASA before leaving there. One point, he was in charge of an $800 million a year program. Also, while at NASA, he was in charge for a number of years of their efforts with regards to space-based solar power, which was later discontinued. He's widely acknowledged as the world's leading expert on space solar power, and is, of course, the star of tonight's TV programs. John?
Thank you, Mark. Thank you, George. Turn that down a little bit. It's nice to see. We should have had a bigger room. I think I've got about 90 minutes, you said? Just kidding. It's rather odd watching these first few minutes of the program because I have not yet seen the final product.
Oh.
And so, in fact, I was very nervous about how it is actually going to turn out. They took something like 30 or 40 hours or more of actual live footage. So I don't know which portions will end up getting edited into it. This morning, what I'd like to do is talk a little bit about the background of the last year, a little bit about the background on space solar power, not much because Mark's already spoken to a lot of the issues. talk about what's been accomplished, so what's going to be presented in the program this evening, and talk a little bit about the path forward, my feelings about what should happen next. So space solar power, as you now well know, is the idea of collecting solar energy in space and transporting it to markets on the Earth. It represents the potential for extremely large scale and virtually inexhaustible, i.e. there's billions of years left in the sun's life cycle, so essentially inexhaustible energy. And the prospects of space solar power, unlike almost any other kind of energy solution that is also green, include dispatchable energy to remote locations worldwide, i.e. the power plant being up in space. You can immediately transform the power relationship between the solar power satellite and, say, someplace in Texas to someplace else, such as New Orleans, if you needed energy to take care of a natural disaster, or to Central America after a hurricane, or you had a power station over the South Pacific, you could immediately reconfigure to deploy substantial amounts of power to an emergency situation such as happened with the tsunami several years ago, and so on and so on. That's almost unique in green energy options. However, there are a number of critical issues that have to be resolved if space solar power is to become a really viable option. So what are some of the systems concepts? Mark mentioned that there are a number of them that does make space solar power robust, and that there are a variety of ways to do it. In the upper left is a concept from the 1970s called the reference system. The next one in the middle top is called the sun tower. That was an option that came out of the 1990 studies at NASA, as is the one to the right of that, which is called the solar disk. And the one below that, which is was known at NASA as the integrated symmetrical concentrator. Just below that to the center right is another concept, which is a constellation of laser-based power systems, and then in the lower right is the sort of the best of breed at the moment that I'll talk more about in just a few seconds, which was also in the video, which is sort of a modular, what's called a sandwich concept, and I'll mention just briefly why it's called that. But in order to become technically and economically viable, space-based solar power, space solar power systems have to have high end-to-end efficiency in terms of the collection of the energy, its conversion, and its transmission, and its reception. Has to have a relatively low total mass. It cannot weigh a huge amount or it becomes economically infeasible. And the ultimate cost to deploy and operate the system has to be feasible. Sort of the best systems concept that I know of at the moment is this modular symmetrical concentrator solar power satellite. This emerged as a concept last year during the study group that was done, the study that was being done for free by a team of folks for the National Security Space Office. Some of you may have been at the press conference that was organized on the 10th of October of last year. Some of my remarks will be about what's happened since then. This modular symmetrical concentrator concept is hypermodular, which I can talk more about. The idea is that you can never get to low-cost systems or operations in space unless you get away from making spacecraft like in onesies and twosies, like the International Space Station has been made, i.e. you make one piece and you never make another one like it except for spares that you might need someplace down the road. You have to get to the point where space is done like modern electronics, consumer products of all kinds are done, like modern military systems are done, where you manufacture hundreds, thousands, tens of thousands, or hundreds of thousands of units. So this hypermodular design is quite central to through eventual economic success. This design is also clever in that it uses this mirror system for power distribution, for the management of the energy on the spacecraft, which is represented by that disk in the lower center. Essentially avoiding having a lot of power cabling. If you've done much with space systems, you know that power harness is a huge issue. The reference system from the 1970s was all hardwired, and so you essentially had a concept where you had to move gigawatts of power on the spacecraft at 10,000 volts and the amount of wiring and the harnesses and the voltage management was just enormous. This strategy gets rid of all of that hardware by simply managing the incoming energy as light through this adaptive optics system, very similar to the kind of optics that are used in the Keck telescope, to distribute the energy as light to where you want it on the transmitting array before you convert it into electricity. So at one stroke, in this concept, you get rid of all of those technical issues. Another is, and that's these large thin film mirrors on either side. Self-assembly is also critical. Obviously, if you've ever gone to a strange place with your laptop computer, you flipped it open, or maybe it's a Starbucks in Tokyo, and you flip it open, and you turn on your Wi-Fi, you have no big issue, everything goes well, you get your IP address, everything gets assigned, and the next thing you know, you're working away at the office remotely. The whole world these days, the wired world, is based on the idea of sort of seamless, adaptive interconnection among these computing machines, PDAs, cell phones, personal computers, household devices increasingly, and on and on and on, without ever worrying about it. Space systems have to be like that if they're ever going to be large scale and affordable. They can't be clean room based, individual design where you've got software software designers and programmers putting together detailed code for exactly what's going to go on this wire. Everything has to go to plug and play. And these systems have to be intelligent enough to be adaptive in their assembly and operation. And over time, not immediately, not instantly, but over time, the systems have to be able to accommodate the introduction of extraterrestrial materials if you're going to go to very large-scale space-based solar power. This design has a number of very elegant features, such as the thin film mirrors, which are very compatible with the easy introduction of extraterrestrial materials, not hard in the sense of having to first put into place the entire industrial economy, someplace like the moon, before you can do anything to get started with energy from space. Okay, so what's happened in the last year? I mentioned the press conference last year for the National Security Space Office. The study which was done for that office, Lieutenant Colonel Paul Damphus from the NSSO is here today. He's the current manager at NSSO for their space-based solar power activities. Next to him is Lieutenant Colonel Peter Garrettson, who is one of the great champions within the Air Force for space solar power. Following this, the press conference and the release of this study report, a group of organizations got together, largely under the leadership of the National Space Society, and put together an action committee, sort of a group to push forward space solar power over the last year. The magazine Ad Astra, which was out on the table, is an example of the kind of commitment that the Space Society has made to space-based solar power as something that should be on the national space agenda. And in the lower right is the cover of the agenda for a by-invitation symposium that DoD organized this last summer, looking at what are the power requirements of the DoD. You may have seen a recent study on energy for the future of the Defense Department that was done by the Defense Science Board. Actually has one little blurb in that report in one table in the back that talks about space solar power. So which is something of accomplishment in a report by the Defense Science Board. But this reflects two things really. One, the increasing issue that the DoD faces with regard to energy to assure operational capabilities and energy security for the U.S., and increasing conversations about space solar power as one option for this. Now, because of the NSSO press conference, I got a phone call in October of last year from a young man at a place called Impossible Pictures in London. And he said, we've got this activity we're doing for the Discovery Channel. You got any experiments you might try to do that would be meaningful and might be part of our new series? And as it happened, we were organizing at that time a workshop out in Hawaii, a joint U.S. and Japan meeting that takes place every year. And I co-chair with Professor Nobuyuki Kaya of Kobe University, a working group on space energy and energy systems. And I said, why don't you come out? And of course, this young man from London, given an opportunity to tell his boss he had to go to Kona, he said, "Oh, damn it, but I'll try. I'll see if I can make that work." So 2 weeks later, he showed up in Hawaii. We talked him through. We plied him with Mai Tais, and in early December, we got down to some serious negotiation. The first week in January, we signed the contract, Managed Energy Technologies, which I'm the Chief Operating Officer of. It's a startup that's focused on novel energy solutions. We signed a contract, and about 4 months later, we did the test. So this was a very anxious 4 months and a week, and very, very challenging. But what we achieved was a first-of-a-kind long-range test of solar-powered wireless power transmission technology, essentially all of the major system elements that would need to be in a space solar power system. And we tested it between Haleakala, about 11,000 feet up on Maui, over to Mauna Loa, over on the Big Island of Hawaii. The distance between the two is about 93 miles or about 148 kilometers. And the test was, I would say, in no way fully successful, meaning we didn't accomplish everything we wanted to. Our eyes were much bigger than our 4 months. That were 16 weeks. We had 16 weeks to do it in, but nevertheless, we did have a successful first-of-a-kind test, which you'll see in the program this evening. I think we've transmitted energy from a realistic device, which I'll talk about more in a moment, about 100 times further than was done in the Goldstone test of 1975. And also, I should say, probably about 1,000 times less energy. If you've ever seen the videos from the Goldstone test, it uses a 70-meter dish of the Deep Space Network. It's got huge klystron tubes, generates about 50 kilowatts of power, and it blasted this across about a mile across this valley in desert in Goldstone, Mojave Desert in California, and illuminated a battery of floodlights. We of course, were working with a much smaller budget, a shorter time, and in the context of the FAA. So we had long negotiations to get FAA approval. Our test is done right in the shadow of the FAA towers, where they do communications for several of the islands. And we got their full blessing. We had them involved constantly every day, and everything worked out just fine. But we had to be very careful that we met their specs in terms of power levels and so on. As I mentioned, the project was about 4 months long. It was less than $1 million, and I think it demonstrated that it is possible to make real progress both quickly, affordably, and internationally. So this just shows the map of the two islands. Just to show you, the transmitter was right here, and the receiver was here. And as you'll see in the program this evening, one of the techniques for the filming, which caused us no amount of grief and technically, was to fly a helicopter back and forth through the beam and take cross sections across the beam to measure its energy. By saying it caused us enormous amounts of grief, you don't fly helicopters for very long at 12,000 feet. And so we were constantly having to stop and wait for the helicopter to refuel or be ready to fly through. Anyway. A number of key technologies were integrated and tested together for the first time, including solar power modules, powering solid-state FET amplifiers with a novel retro-directive phase control system. This is the first time there was ever a field-deployable solar-powered wireless power transmission system. We got a lot of good information about the economics of building these kinds of systems, which is a lot better. Real data is a lot better than speculation about what might these things cost, especially going forward. As you well know, is sponsored by Discovery Communications. The key participants, in addition to myself, were Professor Nobuyuki Kai at Kobe University. He's a great leader in microwave wireless power transmission. He's worked in the field for many years. Frank Little and Professor Kai Chang from Texas A&M University provided the U.S. side of the power beaming system. There were a bunch of students at both universities who worked like dogs for weeks at a time. And I might mention, right in the middle of this is graduation, is the end of the school year in Japan. So at the beginning, in January and February, we had one group of students from Kobe University. In April and May, we had a different group of students. And so that was very, very challenging for Professor Kaya and for his technical staff from his lab. They were just pulling their hair out because here you start with one bunch of kids. You'll see it in the show. Maybe you'll see one bunch of kids first part of the filming and another bunch of kids later in the filming. Then you had to start over and get all the other kids excited and working hard. And also Dr. Neville Marswell from Caltech participated in the solar power module design. This is the hardware. Essentially, there's a set of transmitter panels. What you see here are receiving patch antennas that were intended to receive a pilot signal. Each of these is a transmitter patch antenna. 8 of them turned out to be used on Haleakala. 9 were fabricated to make a 3x3 array, which was used for testing in the lab. We discovered a lot during the course of the project. One of the things we discovered was that the received power from the pilot generator was going to be much lower than we thought it was going to be. And so we had to go from using the patch antennas to using these TV dishes to set them up to concentrate the incoming pilot signal to guide the beam formation. The solar power module, which generated a couple of kilovolts, we were belt and suspenders all the way, even though it turned out we had a beautiful day and there were no issues. Since we couldn't afford to fail, we had a power management system with like 3 kilowatt hours of power storage and power management and distribution. So solar energy came in from 6 panels, got distributed out to 9 panels to power the transmission experiment. And you can't see it very well, but part of the test, which you'll see in the show, has to do with a short-range test across an airfield, an abandoned airfield in Maui, which all had to happen the day before the mountain test. I might say that you can't leave stuff out on Haleakala. It's sacred ground. And so everything that we set up had to be taken down every sunset. Nothing could stay overnight. And so over the course of 3 days, we built everything 4 times. We put it all together, and this is all shipped in from Texas and shipped in from Hawaii, and we put everything together in this warehouse that we rented to use as a lab. And of course in the lab, everything worked fine. And then we had to tear it all apart and truck it to this airfield, and then reassemble it all, and then make it work with the wind blowing and chairs going over and just dust everywhere, and make it work there. Then we had to tear it all apart, and the next day we had to take it up to the mountain and see if everything was going to work there. We put it all back together again, but it all had to be torn apart that night because we couldn't leave it up overnight. And then finally, the day of the real test, we had to put it all together again. And so by the end of the 4 times around, which is 4 times in 5 days, we were stretched pretty thin. Each of the panels was designed to put out about 20 watts. In order to conform with FAA standards, we actually operated at about 2 watts per panel, so the whole thing was about 20 watts. So it was a lot less power than we had wanted to use, but again, getting FAA approval was critical to success. So they had no concerns about it. We ended up getting approval from the State Communications Organization, from the FAA, and from the Maui PD, and everybody ended up really happy with the test, and ultimately wrote us notes and basically said, how's it going, and good luck, and hope the wind doesn't give you troubles. And that's nice when you get that from a regulator. What we accomplished in this is essentially to build a solar-powered, phased-array power transmission system with active phase control in 4 months with less than $1 million. Our capacity to transmit was only about a couple of 100 watts, and when we ultimately operated, it was only at about 20 watts. As you'll see this evening, we had no amounts of troubles and grief and problems. They were worried at the beginning. They said, this is just electronics. Is it really going to be interesting? And maybe we need to script in some problems. And but no, it'll be fine. They didn't have to worry about scripting anything in. I think if you went to anybody in the business and you said, I'd like this and this is your spec, and you put out a contract, before this year, what you'd have basically said is this is like a $10–20 million effort, and it's going to take at least 2–3 years, and it's going to be this and it's going to be that. So less than $1 million, 4 months flat. It is not intractable. And the reason it was not intractable is the same reason that space-based solar power is not unthinkable, and that is we came in with a basic design and we fabricated a number of them. And so it was not a question of building each single panel with a unique design. We came up, we could have made 100 panels with another $1 million, because we could have taken all the designs, all the circuit board designs, all of the stuff that had been done, and go out to a small contractor and get a bunch of these things made. So these kinds of technologies, because they're very modular, scale up very readily. So where to next? What we think we've done is to demonstrate that progress is possible. It's possible in a short time, and it's possible at a reasonable budget. We think what needs to happen next over the next couple of years is, and probably for less than $100 million or so, is to do a legitimate systems, end-to-end system study. I'm going to talk more about this in just a moment. We call it a quick look study. And to start validating a number of the key technologies for space-based solar power. Within 6 or 7 years, we think that economically viable architectures can be well-defined and designs matured, and we can get to major flight tests of space-based solar power in low Earth orbit. Within the next 10 years, and this is consistent with the roadmap that was presented to the NSSO last fall, and for less than about $10 billion, we think that you can get to a legitimate pilot plant in geostationary Earth orbit, and the validation of the key space transportation technologies that will be necessary for space solar power to be economically viable. And within 15 years, we believe that you can get to the actual deployment of operational systems. So the next couple of years, first this idea of a quick look study. Nobody has done an end-to-end system study that in the public domain on space-based solar power in the last 10 or 12 years. The last one that was done by NASA. It was the Fresh Look study. It was done between 1995 and 1997. And so if anybody comes in and says all the analysis has been done, we don't need to do any more of that, it's just false. So there is an absolute requirement for more and for rigorous and independently reviewed systems analysis. And the analysis needs to be both tested experimentally. Key assumptions need to be tested experimentally at the component level, and there needs to be independent review at the National Academies level. The validation of key space solar power technologies doesn't have to wait for that study. It can proceed in parallel with that study. And of course includes repeating and upgrading. You're going to see, again, all the problems we had in 4 months. There's a lot of things that didn't work out the way we had hoped they were going to work out. So that experiment needs to be redone, upgraded, improved, and so on. And the panels need to be redesigned, re-engineered, and it's not an unimaginable amount of money to do that. At the same time, there's a need to develop and test other key technologies. Wireless power transmission is not the be-all and end-all. It's not the only technology. It's the most visible technology for space solar power, but the physics of it is relatively well understood. The solar power generation and getting rid of the waste heat on the platform and doing so in a low mass way, something that doesn't weigh too much, that is absolutely critical to success at the systems level. Being able to do higher efficiency wireless power transmission with solid state devices that can handle high temperatures, putting together not just a little demo at MIT. Have you seen Spheres at MIT? It's a great lab up there, the robotics lab, and they've got this test going on Space Station. They've got these little robots that are shaped like balls that basically fly in formation. And there's another one at USC where you've got these little modules about the size of your fist, and it's called the Superbot, and they can put themselves together in different morphologies to make a worm or a snake or a rope or a quadruped, on and on and on. There's all these different architectures, all this brilliant technology being done in these different places for free flying, constellation flying, close proximity maneuvering, self-assembling machines. All of that has to be brought together in a series of tests to validate the architectures for this kind of system application. And the space transportation technologies such as solar electric propulsion. Again, I don't think any of this is out of reach. None of this is, the invention or the discovery of high temperature superconductors or carbon nanotubes, but it's not going to happen for free. And there needs to be, even during the next couple of years, a meaningful start on developing and flying technology flight experiments that test these key concepts. So what are the hazards to avoid? Just right quick. One, the assertion that it's impossible. If you look at the cost of current space systems, it'll cost trillions. Well, obviously, if you tried to build a Swiss watch the size of an aircraft carrier, an aircraft carrier wouldn't be a $5 billion project, it would be a $500 trillion project. You don't build aircraft carriers that way. You don't build server farms that way. You don't build all the things that we use in modern society, you build them that way. So you can't do anything large scale in space if you try to do it using the current spacecraft approaches and manufacturing approaches. And just a general belief, you can never, yada, 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 whatever it is. It'll take 50 years. I know the NSSO report was a little more conservative. It said it's going to take 40, 50 years. You know, maybe. I absolutely do not believe that's true at this point, because I think that if we're successful in solving the key technical or engineering problems, I think the solution can be at hand according to the roadmap that I described a moment ago. Another is it'll take 50 years because we can never do anything until we get to $100 a pound space launch. If you're interested, I published a paper at the recent AIAA IECEC conference, that's International Energy Conversion and Engineering Conference in Cleveland, looking at some of these issues. The bottom line is you don't need $100 a pound for space launch to get started. It would be nice to have eventually. You need very low cost launch, but you don't have to have it immediately. Another myth, don't succumb to analysis paralysis. And the storyline is the hazard to avoid is we don't need more studies, let's just do hardware. All good engineers hate doing studies, they always like doing hardware, and the last thing they want anybody to do is to poke at their design choices. Certainly not anybody in the public domain. None of them who are laymen should have anything to do with design choices. In fact, no end-to-end studies have been done since 1995, 1997. They absolutely need to be done to get at what are the real parameters that we have to achieve. How light, how hot, what kind of energy conversion efficiency is enough, how expensive, how to assure beam safety and control, and on and on and on. And lastly, the temptation to do meaningless stunts. There's an old vaudeville joke that was very popular in Rocky and Bullwinkle, which is Rocky comes along and Bullwinkle is in the gutter looking for something under a street light, and Rocky asks him, what are you looking for? And Bullwinkle says, I'm looking for my wallet. Rocky tries to help and says, well, where did you lose it? I lost it down that dark alley. Well, what are you doing over here? The light's better. Similarly, it's very easy, it's very tempting to say, let's move forward right now with a test that we know we can do. Let's use lasers, or let's use 94 gigahertz as another popular example. It's high frequency, the antennas will be small, it'll be much easier to do than doing it at the right frequency. The dilemma is it doesn't get you there from here. You could do such a test, you could spend a huge amount of money, it doesn't actually make any progress towards solving any of the real technical problems. That's the problem. It's easier to do, the light's better, but the problems are down in the shadows. And we need to get the light shined into where the shadows are and solve those issues. So in conclusion, space solar power has the potential to generate hundreds or thousands of gigawatts of clean and sustainable solar energy from space. The question is at what cost and how safe and how hard is it to do. The major challenges are fourfold. It's certainly perception, establishing space-based solar power as a viable option. It's technically viable. Policy, creating the right framework of government sponsorship for longer-term research and development projects. In engineering, it's demonstrating the means to economically viable space solar power. And it's commercial. It's establishing a commercial foundation to not pay as you go, but profit as you go. Companies don't want to pay as you go. They want to profit as you go. And so if you're going to come to a viable scenario over a 10, 15-year time frame, companies have to be able to make money as you go along, and they have to get their own skin in the game. They have to make their own investments. So coming to that framework is critical. I believe that these challenges are neither insurmountable nor trivial. They are solvable, but they're hard. The demonstration was in May was a beginning. It's really hard to live in the terms of my contract for non-disclosure and not telling anybody for months. So that was very difficult. So I'm glad that's over. Real progress was made. It was done fast. It was done at an affordable price. What do we need now? We need this quick look study for end-to-end systems analysis. We need initial technology R&D and demonstrations. We need to focus on the technologies that need to be proven, not look out where the light is good. not do easy stunts, but do the real technology demos and real experiments that lead to solving problems that need to be solved at systems level. And we need to make real progress to push forward to a pilot plant within a reasonable time frame, or it'll never get on anybody's political radar. It just won't be an issue if it's always a 50-year away kind of thing. Yeah, don't bother me with that. OSTP and OMB don't listen to that kind of conversation. So, thank you very much.
Let me just make a brief point that was suggested by Peter Gerritsen, and that it's fitting today that a great number of lives are being saved because of space technology down in the hurricane zone. And we are also talking about a technology which has the potential of lifting out of poverty a large fraction of the human race, and as a consequence, saving a great number of lives as well. Now we're going to take just a few questions for John Mankins. We'll have more questions at the end of all this. We have a surprise speaker which will come in for a moment after we take a few questions, which will talk about some of the congressional implications of all of this. So, John, we'll be here. How about some questions? Yes.
Can you tell me what kind of fraction of energy from the transmitted beam? In other words, the efficiency. You send 20 watts. What did you receive? Because that's a key question here. And if you were sent 20 watts, even if you received 20 watts, that's not even enough to light a light bulb in my house. What was the size of the receiver here? Because that's a big issue. How long did this hold the beam last, and why not? What's wrong? How is this? You're talking about not a stunt. This seems like the very thing they're saying not to do. How is this not a stunt?
Okay. Yeah. Sure. So the answer for this particular system, because of the cost constraints, the panels were good, realistic panels. The devices were good. We used, as I said, FET amplifiers. But projected efficiency, where we think we can get to end is about 64%, something like that. Where we are right now is nowhere near that. As I said, what we did was to take essentially a slice of what should have been a circular transmitter. A circular transmitter would have been over 100 panels. We'd have money for 100. In order to get good focusing in one direction, in one dimension, we made it a linear array. And so that meant that vertically, the power just went up and down and spread wildly. So the actual end-to-end efficiency was terrible, was extremely low.
What was it?
If we transmitted 20 watts, I would say that we received fractions of microwatts. Fractions of microwatts. It was tiny. And
so less than 1%.
Oh, no. Less than 1,000th of a percent.
In terms of efficiency.
Yeah. But again, that wasn't what we were trying to do. When we took the equipment to the lab, we set it up at short range and tested the transmission of the beam over 12 feet, over 3 meters. Very good efficiency. We were like 40% efficient. We had set up the rectenna. We had good beam coupling. It was with a square array. It was in short range. It was like 40%. So if we had a large enough array, same exact technology, with a large enough array with enough money, but all the same exact technology, same components, then you could have seen that kind of efficiency. On the other side, by the way, on the other end of it, another reason why it was so low, it's not because the energy wasn't there, but our receiver was so tiny. I mean, the receiver was about my size, at a distance of 100 kilometers. I mean, so the beam itself was spread over miles because the transmitter was so small, but the receive power was very tiny. So it's not to say the power wasn't there, and one of the ways we got at that in terms of the experiment was to fly through the cross section of the beam. So we had a small receiver, as I said, not a lot of money. To see where the energy was, they flew through the beam and took cross sections to see the shape of the beam by flying across it. But because of the linear decision, which is just strictly budget, not technology, but budget, the energy above and below, and I could actually show you what our calculated beam pattern was. it basically looked like this. So all the energy above and below was spread, and it was focused into a relatively tight central lobe. So the reason why it's not a stunt, though, just to come back to that last part of your question, the reason why it's not a stunt is these are the right component technologies and the right kind of system architecture end to end, i.e. solar to voltage to FET amplifiers to microwave to receiver. So end to end, it was all the right kinds of technologies. It was strictly a matter of budget that kept it from being a higher power test.
Yes?
What you mentioned the right frequency for this. What is the right frequency? What frequency did you use, and what is the right frequency? And just if I could just ask all my questions at once, are there any patent issues involved in any of this? And finally, are you in touch with any of the either of the presidential candidates? Since this does seem like it's going to be, at least right now, it seems like it's going to be an issue in the coming administration.
The answer at the moment is, to the last question is no, I'm not personally in touch with either of the presidential candidates. I'm an old friend of Lori Garver, who's a space policy analyst and advisor to the Democratic side. I don't know anybody, I just don't happen to know anybody on the McCain side. I've just known Lori since she was at NASA headquarters in the 90s. There aren't, I'm working backwards, there are no IP issues with regard to this experiment, other than perhaps some of the detailed circuit design things, but you're not going to see any of them on the show anyway, so this doesn't represent a public disclosure. But the basic concepts and so on have been around for some years. What was the first one?
Right frequency.
Thanks, right frequency, thank you. The frequency that we used was 2.45 gigahertz. That's very popular because it's about 12 centimeters or so in wavelength, and atmospheric water vapor and clouds and rain and so on, it's transparent to that wavelength, so there's essentially no losses. That gets you to 24/7, which is critical to, and very, very high transmissivity of the Earth's atmosphere. Another one that we're looking at very seriously is about 5.1 or 5.8 gigahertz. It's only a little bit shorter wavelength, like 3 centimeters. It's very attractive because most of the atmospheric condensation or water vapor and so on is still transparent at that frequency, but everything gets much smaller on the ground. The receiving antenna can be much, much smaller, factor of 4 smaller. The range from about 2 gigahertz to about 10 gigahertz is a good range. One of the big considerations about how to get to the right range is making sure you do no harm, so you have to be cautious about other uses of spectrum. The final choice of a part of the spectrum would have to be worked with the International Telecommunications Union and have to work with the radio science community. I was at a conference in Chicago last month with the radio science community, their every 3-year meeting, and they were very interested not only in this frequency itself, but also in the harmonics. So higher frequency harmonics, you're going to transport at 2.45, you're going to get a harmonic at 4.9 and another one at 9.8 and so on. The one that looked pretty good for them was about 5.8, because then it turned out the harmonics were out of what they were interested in. But that's a to be done. That's one of the things that you do during the system study. When you go to higher frequencies, like you go above about 10 or 20 gigahertz, like with KU or Ka band communications, the atmospheric losses due to water vapor are much more severe. Up around 90 gigahertz, there's a window, but even in that window, you still lose about half the energy that you try to send through the Earth's atmosphere. You can't make any scenario work if after you do everything and when it's almost at the receiver, you lose half the power. So that's the reason to stay at around 2 to 10 gigahertz.
Okay.
Could I just, one clarification, you negotiated this with the FCC, right?
What we did was we looked at the FCC rules and the power levels involved, and we were experimental. We weren't going into operation anywhere, and we were fully compliant with all the OSHA regulations and everything else.
But you didn't have to talk to the FAA?
Well, no, the FAA we absolutely did, because we're operating in the vicinity of their equipment.
Oh, I see.
Okay, since this is a press conference, let's keep the questions just to the press for at least for a while. So, yes.
Marilee, Washington Business Journal. So, Discovery paid for this experiment, is that correct?
With the caveat that there was a great deal of donated time.
And have you gotten any government grants that managed energy technology? Where would you get this $100 million from? And are there any big satellite companies or solar companies working on space solar?
There's a fair amount of interest in working organizations and business units and so on among some of the major aerospace firms. Obviously, I'm not going to speak for them. I will say that managed energy accomplished what it did through a teaming effort. So we had a team of folks at Texas A&M, Kobe University, and so on, who were working with us. Our strategy to work in the future would be in the same way, and we're in discussion with various primes about the kind of relationship we could have with them.
You mean other academic groups?
And I mean the prime contractors, the big firms. I'm doing it backwards doesn't work as well as doing it forward because I forget what the question was just upstream.
Where would the 100? Have you had any government grants
we
yet?
We have not. Yeah, we have not yet had any government grants. We're as Mark mentioned earlier, there's currently no U.S. government program for this. There are some in-house efforts that have gone on. There was the study that was done for the NSSO last year. We're certainly hoping that that situation is going to change, and we see potential activities and interest both at the Pentagon level, for example, in the National Security Space Office. We have folks also in the Air Force, certainly also in Navy, ONR, and so on. There's a lot of partnerships in advanced technology, advanced space technology between Air Force and Navy. Certainly power beaming is of interest to the Army. We think there's potential for technology interest on the part of NASA, certainly. And there's a lot of related technologies within the Department of Energy. So if there were to be in the future an ARPA-E, that might be a very legitimate place for a lot of the component technology work to be done. So we think that the $100 million could happen in a variety of places. But the key thing is to have it actually focused on these problems.
And you don't have any venture capital either?
Not at this time.
More press questions? Yes.
Heather Fortune-Weaver with Satellite Week and Green Electronics Daily. On the satellite side, at the LEO, how many would you need? And then, would you do it with just one GEO, or would you need several?
You probably would never do an operational system in low Earth orbit because the contact time is so short, and to be able to do the beam steering, you lose a lot. So your actual time when you can beam power efficiently is a couple of minutes per pass per satellite, and so those numbers don't work out. So you do LEO for testing and for validation. The strategies with this hypermodular is very much like if you were to look at the Iridium constellation, but instead of having those satellites distributed around the world in these different orbits, they would all be together and they would operate as a single contiguous phased array. And so the sort of this hypermodular strategy would be to build very large space systems out of literally thousands and tens of thousands of networked small satellites, small to medium-sized satellites. So in geostationary Earth orbit, you would really need basically a large number of platforms. One platform nominally is a couple of gigawatts, a couple of thousand megawatts. That one platform would represent 1,000, 10,000, 20,000 smaller elements. So if you imagine all of the PCs in Washington, D.C., they operate in the internet, they operate in a network computing framework, same kind of strategy for these very large platforms.
I guess what I don't understand is if it's beaming down from GEO.
And there would be a lot of them.
Oh, yeah, you would need them.
You bet.
Okay.
You would need a lot of them. And one of the architectural options we looked at a decade ago is not to put it precisely in GEO, but to put it near GEO. So there's actually a lot of territory that you can use because it's an active phased array. It's not a passive or mechanically pointed dish antenna of that type, like a lot of conventional satellites in GEO are dish antennas. So with a phased array, you can actually look at a wider range of orbits near geosynchronous Earth orbit.
Just one last one. How many to cover CONUS? Just so I can give an idea of how many satellites you would need.
It depends on the size, but
okay.
For one caveat, just you'd never ever make the argument that you would provide all the power of the U.S. from this one source.
Okay.
I mean, I'd never make that argument. You'd always have a portfolio. You'd have you'd go ground solar everywhere you can put it. You have all sorts of renewables. You have 20% wind. You have, but you bring in 10 or 20% from this source, and it helps you a lot in your distribution and the management of the power load.
Yes.
Krista Marshall with Climate Wire. There's been some concern about the safety of microwaves being beamed down from space. Is that something you could test at all with this study, or because the transmission was so different on land, it wasn't something you could look at, or no?
It wasn't something that we could test in a rigorous way in this particular project. We certainly had a documented health and safety plan. Our best estimates from past research is that our power levels in these frequencies are completely benign, and the exposure levels are small and the times are short. So we had no particular concern. We still had a good safety plan. We still marked out our terrain. We stayed out of the front of it. It was more belt and suspenders than any real concern. In order to get at this, you'd need to make health and safety and environmental related studies part of a future R&D effort. And there's some very nice work that was done out at the Ames Research Center in the late 1990s, which I could provide you a reference on, looking at the impacts of low-level microwave radiation on plant species, basically alfalfa. And then back in the 1970s, and Alan Legg was here, who was involved in the studies in the 1970s, looking at animal species, such as bees and so on. And all of the studies suggest there's no effect whatsoever of any kind of mutagenic kind. The wavelengths are too long, but you get some thermal warming. And one of your biggest issues would be that species would tend to migrate because they'd like the warming. So there's no impact, pun intended, like there is in the case of wind turbines, where you've got a device, you've got a mechanism which directly impacts local species. It's just there's going to be thermal warming, and there'll be some long-term effects, and the basic issue would be to keep birds off of it in the wintertime.
Okay, we have a surprise speaker which we're going to bring up now. This is Paul Rankatori. He's a former candidate for Congress, and I think there's a good probability that he'll be a candidate to become a member of Congress again in the future. Paul?
Great job, John. That's the best presentation. My district was Florida 15, which represents a very strong portion of NASA, which is Cape Canaveral, Patrick Air Force Base, Kennedy Space Center. I think we all can agree, at least it's a major part of my platform, that energy is probably the biggest issue facing the country as well as the world. And in order to achieve and understand what we can do for our energy needs, we have to have a short, mid, and long-term plan. And I have couched this in a big phrase calling and trying to create a paradigm shift. If we don't understand and really embark on a process to create a paradigm shift with our energy needs, how we develop and consume energy, we're going to be back in the same situation, 5 years from now. Right now, there's a lot of folks talking about drill, drill, drill. Well, if you don't couple that with sound strategies for the long term, we're never going to move forward as a society. And in my case, in my district, we're also going to suffer economically. So what space-based solar power does, in my mind, solves three of the major issues facing the country and possibly the world. Number one, the economy and jobs. My district is going to lose up to 24,000 jobs when the shuttle retires. Starting this October, we're going to start seeing that job loss. And this potentially has the opportunity to create about 800,000 new jobs. Secondly, it changes our whole focus on energy independence. Although we do have resources in our own country with respect to oil, we have to look beyond that. And space-based solar power actually helps us create a paradigm shift. And if we don't focus in those terms, we're going to be just mowing the same old options about corn-based ethanol, which for those of you know, that's probably the most inefficient, corrosive, and environmentally damaging way to make ethanol. But we're still back on wind and solar. Space-based solar power is an element of a long-term strategy. It's not the panacea, but it's a strong element of our long-term goals. And unfortunately, our country likes, we like to think about something, what's going to happen tomorrow? We're so reactive, we want instant gratification. So when we look at this, we have to look at this from an inspirational perspective, about a job perspective, but also foreign policy. We're in places in the world right now we shouldn't be in, but we are because of dependence on oil. So space-based solar power provides us creating that paradigm shift. It helps us with jobs, it helps us with energy independence, and lastly, it changes our foreign policy, which is tremendously costly to our country as well as the world. If you get anything from today's presentation, I'd like to leave you with this, is don't be focused on drilling down, focus on drilling up. Our goal here is from a congressional perspective, my perspective, is I'm working with speaking with the members of the Energy Committee as well as Select Committee on Global Warming to educate members about what space-based solar power can do for our country, create that dialogue, and possibly create a space-based solar caucus within Congress for them to understand fully the ramifications for our country and the world, and start getting members involved. Because right now, the only dialogue that exists is about drilling or not to drill, or we're going to start burning switchgrass tomorrow, and that's going to solve all of our needs. And it won't. We have to elevate the debate. We have to elevate members' awareness of what exists, but also where we need to go for our country. And space-based solar power does that. So with that, I want to thank you very much for inviting me. And if there's any more questions, I'll talk about later after the conference is over. Thank you.
Thank you, Paul. With that, we're going to close the press conference. Paul, myself, and John will be around to answer additional questions, probably as long as you want. So thank you for coming, and hopefully we'll move ahead on this very promising technology.
So, why did NASA abandon the space or what did they want, and why would that be something that made them stop?
So we did try
is of such tremendous importance to this country and potentially the world. Space solar power, we have a little demo up here, which is on a loop. Basically, there's a lot of different possible architectures, a lot of different ideas about having space solar power, which is one of the strengths of the concept, because that means that if one of these approaches doesn't work out, we can try another one. Sort of base case situation is demonstrated by this video. You have solar cells in space. They collect energy from the sun, convert it into a very low intensity microwave beam, and then send it down to the Earth, where it's collected on a rectenna, and then this is fed into the power grid and gives us electricity. And I'll walk you through it on the next loop here. One of the things which, yeah, here we go. This is one concept of space solar power. And in this particular concept, we not only have solar cells, which are down here, we have mirrors in space, which concentrate the energy of the sun onto the solar cells. And the reason for that is the mirrors are relatively inexpensive, and the solar cells are relatively expensive. As a consequence, if you can concentrate some of the sun's energy on the solar cells, then that makes more economic sense. The power comes down, actually not in these loops. It hits the rectenna, which is that green thing, converted into electricity, and it goes over to the city to power it. Could you turn off?
Sure. We'll turn this on.
Yeah. I think we've seen that a number of times. One of the questions which frequently comes up is how to turn it off.
It's relentless.
There's the plug down there.
No, don't pull the plug. I need the plug.
Don't pull the plug. Sorry.
If you pull out the headset jack.
How about escape?
Yeah, the picture's okay. Sound.
Or just mute it. The laptop.
You will write what I tell you.
One of the questions which frequently comes up concerning space solar power is, well, look, it's clear that doing things in space are more expensive than doing things on the ground in general. So why does it make sense to put solar cells in space rather than on the ground? And there are basically two main reasons why this may well make sense. One is that the intensity of sunlight in space is a lot greater than it is on the ground, roughly a factor of 7. And the reason for that is first that when the sunlight goes through the atmosphere, you lose some of the energy. And secondly, there is, at any given point on Earth, from time to time, you have bad weather, and as a consequence, you get less solar energy. And the third reason is because you have the day-night cycle, and you obviously don't get solar energy during the night. In space, you have The sun shines on these space solar power satellites virtually 100% of the time. And you obviously don't have bad weather, so, or an atmosphere to deal with. So these problems don't exist. The other big thing is that if you have a power grid on the Earth, and it's mainly based on solar power that's on the Earth, then that means you have to store a great deal of energy in order to take care of your energy needs at night and during periods that are hard to predict of poor weather. But if you have a space solar power satellite, since you're sending on the power all the time, and this beam is at a frequency which will go through bad weather without any significant problem, then you don't have this storage issue. Now, one of the main reasons that space solar power is of such interest is because of its enormous potential size. The amount of power which can be produced by space solar power is potentially greater than that of all the other energy options combined. And it's quite sufficient to take care of all of our current energy needs, for not only this country, but the human race. I'm Mark Hopkins. I'm Senior Vice President of the National Space Society. And this press conference is being organized basically for two purposes. The first is to provide support for the Discovery Channel's TV program on space solar power. And this is going to be broadcast for the first time tonight at 10 p.m. local time. And so you can watch that. It's a very interesting program. The second reason is because the National Space Society strongly endorses the basic concept of space solar power as something that we should look into because of its enormous potential for the United States and for the world as a whole. What we're talking about here, the core of this, of the Discovery Channel program tonight, and also this press conference, is a demonstration of space solar power technology, which has been kept under the wraps until now. I won't discuss this in any detail because we have the person who led this effort, John Menkins, here, and he will be discussing this a little bit later. What I'm going to do is give a brief description of space solar power, the overall architecture, and then I will discuss why space solar power, if it works out, as a whole. And to continue to do that, even if the demands for energy, as is likely the case, increase substantially over time. There's also the potentially the greenest of all the energy options, maybe even greener than space-based solar power. I mean, ground-based solar power. And on the long run, that is even more true than in an early situation. And for example, the case, it has very low carbon footprint, and as a consequence, has no significant impact on global warming. Indeed, if we were consuming only space-based solar power today for energy throughout the world, it's highly likely that there would not be a climate issue. Let's look at the larger picture and see how space solar power can really impact the future of the human race. The average per capita income in the world today is a factor of 7 below what it is in the United States. Sometimes we in this country don't quite realize how poor most people are. Now that's the average, factor of 7. That's like factor of 2 below the poverty line in the United States. Poor people, by human standards, are a lot worse off than that. In fact, the bottom 1/4 of the human race doesn't even have electricity. Think about that. Doesn't even have